Alright, so we're going to start with an example of a common source amplifier. Cascading into a common drain amplifier. Alright, so our circuit schematic looks like so. Now I'm going to draw a bulk connection for the NMOS device, and we're going to ground the bulk. The output of this amplifier feeds into a second stage that's going to be a common drain stage. Where we're going to ground the bulk, but in this case we're taking our output off of the source, so we can't ground it, so we're going to put some resistance, our $sign, in the source, and we're going to take our output at this point. Now, one thing that I'm going to point out is that this is going to cause our inspection analysis formulas a bit of a problem, the source not being tied to the same voltage as the bulk, and we'll look at why in a moment. But just remember that this source bulk connection not being equal not being short-circuited is going to be a problem. So what we want to do is find R in, R out, the resistance looking into the circuit, the resistance looking out of the circuit, our voltage gain equal to VO over VI. These are things that you'll commonly need to know as far as what the impedances are at the interfaces, so how will your circuit interact with other circuits, and what will your voltage or current gain, for instance, be. Now the first thing that we have to do is replace our large signal model with a small signal model, and so all that means is that we're going to short circuit the voltage sources. So for instance, our voltage source here becomes a ground, our voltage source here becomes a ground. And we're going to find V out over V sub n, and we're going to say that it's equal to V gate of the first stage divided by V sub I. So this node would be V gate of the first stage. The second node we're going to label V2. So we're going to say that the second gain that we're looking for is V2 divided by V sub I, or sorry, V gate 1. And we're going to say that the third stage, V, is going to be equal to VO divided by V2. So all we need to do is find the gains from each position, 1 to 2, Vn to V gate 1, V gate 1 to V gate to V2, and V2 to V out. Well, because the MOS device has infinite impedance looking into the transistor, we don't have any voltage gain at the for the first stage, so that V gate 1 divided by VI is simply equal to 1. Now we can recognize that the first stage is a common source amplifier, and we know that our general gain formula for our common source amplifier is equal to minus GM divided by 1 plus GM times our $sign. And we know that the next stage is a common drain amplifier, V out divided by V2. And we know that our general form here is GM times our $sign divided by 1 plus GM times our $sign. Okay. Now, for the first stage, we know that there was no resistance in the source, so this term goes to 0. So our whole gain expression can simply be written as minus GM RD times GM R dollar sign divided by 1 plus GM R dollar sign. Now, I mentioned a moment ago that our bulk connection is going to be a problem, and so one thing that we might see is if we were to plug this circuit into a simulator, we would probably get an error, and the reason that we would get an error is the bulk is not tied to the source. And in a MOS device, we actually have a third parameter, or another parameter that we haven't talked about, called the backgate transconductance. And we usually label this as little GMB. So we're going to show you a modification to the pi model here really quickly for a MOS device. So for our transistor, where we can't tie the bulk and source to the same voltage, like in this common drain configuration, our small signal model looks very similar to what it did before. We have our gate terminal, some gate to source voltage. We have our GM VGS and our R sub 0, just like we did before. But we also have another current source, and this current source has a value of GMB times VBS, or the bulk to source voltage, GMB times VBS. And here is our source terminal. Of course, this was our drain terminal, where we're taking our output voltage. We have a resistance here, and we have a bulk terminal now that we see from this figure is grounded. So this difference in voltage between the bulk and source terminal is labeled our bulk to source voltage. Now, if we write KCL at the source node, so we're doing KCL at the source, we find this equation. And I'm going to use a couple of substitutions. I'm going to say that GS is equal to 1 divided by RS, and I'm going to say that GDS is equal to 1 divided by R sub 0. So I'm going to write this expression in terms of conductance rather than writing it in terms of resistance. So here we have 0 is equal to, we have a current flowing into the node, so I'm going to use convention and say that that's minus GM times VGS plus V out, the voltage at the source that we're looking for, times G sub S plus V out times GDS plus V out times GMB. And now we can solve AV is equal to VO divided by V sub I. V sub I is equal to VGS. And if we solve this equation, we would get GM divided by GM plus GMB plus GDS plus GS. Okay, so we're going to assume a couple of things. One, we're going to assume that Rs goes to infinity. This would be like in a case where we biased the source with a current source. So for instance, we replaced, instead of using R sub S, we had a current source here. So just for the time being, we'll assume R sub S goes to 0. And the other thing we're going to assume is that GDS is much smaller than GM plus GMB. And this is also something that we desire. We would like to have large transconductance in these transistors, and we'd like to have the output resistance of the transistors be very large. Well, correspondingly, that would mean that the GDS, or output conductance of the transistors, was very small. So if we make these two assumptions, we can simplify AV to be approximately equal to GM divided by GM plus GMB. GMB is a process constraint and is given by the following formula. GMB is equal to delta divided by 2 times the source to bulk DC voltage plus 2 times phi sub F. So it depends on a DC voltage and then 2 process parameters, this gamma and this phi sub F, which is a work function. We don't need to know the device physics. What we'll typically say is that GMB is approximately equal to 10% of GM. All right, so in the next couple of slides, we're going to modify the small signal model, or we're going to show you how to eliminate the backgate effect. And if you can't eliminate the backgate effect, we're going to show you how to deal with it in the inspection analysis calculations.